SwayamPrabha. Digital India. Educated India.
Hello and welcome to this lecture on robot specifications and robot programming. So what we have studied so far in this course is very ideal in the sense of inverse kinematics, then control, then trajectory planning. These are all extremely ideal. Now what I mean by that is that when we are saying that we are doing inverse kinematics for a position and orientation of the end effector, and we are computing the joint angles, and then the controller is moving the robot manipulator by those joint angles to take it to the desired position and orientation. We are making the assumption that it is exactly reaching that position, okay, or the controller can exactly cover the amount of angle that is required to take it to a desired position and orientation. But we'll see that there are actually a lot of errors in the system, because of which it will not reach exactly that position, but it is going to reach somewhere near that position. And a robot manufacturer has to specify how good his robot is in terms of these errors. And there are three terms which are used. One is called control resolution, then we call special resolution, accuracy, and repeatability. So today's class will look at these terms, mainly resolution, accuracy, and repeatability, and then move on to robot programming. Now, of course, a person buying a robot may not know enough robotics to do programming in terms of controller design and things like that. But there should be an easy language where the manufacturer or easy language which the manufacturer can provide, which the user can use to use a robot. So that is a language which is called a robot programming language. And we're going to talk about VAL2, which is currently used by most industrial robots. So today we'll talk about robot programming, and then we'll move on to we'll talk about robot specifications, and then move on to robot programming. So whatever we have studied so far is very ideal in the sense that we have a robot manipulator here, and we are making the assumption that if I want to go from one position to another position, I'm here, and I'm here. Okay, so this is my position 1, and I want to go to position 2. So what the manipulator will do is it is going to it is going to compute the inverse kinematics in these two positions, right? Find out the various thetas. Okay, so it's theta 1, theta 2, theta 3. In this location, it is theta 1 dash, theta 2 dash, and theta 3 dash. And then what it will do is for a respective joint, it will do theta 1 dash minus theta 1 and generate an error, say del E. And the controller then will design a PD, a PPD, or a PID controller. This is something we have studied in the last few classes, which is going to make this error go towards 0. But in the process, what we'll see is that there are a lot of errors which are inbuilt in the system, and because of which the manipulator may not be able to make this error equal to 0 and may not be able to exactly reach that position. So these are some of the terms which are used by the manufacturer to specify how good a robot is. Now let us look at, so these are the three terms that are used for specifying a robot. One is the control resolution, which the manufacturer has to tell, accuracy of the system, and repeatability of the system. Now in terms of errors that are inbuilt in a robotic system, what are the errors that are inbuilt? For example, control resolution is the encoder resolution. When we studied encoders, we saw that this is an encoder, okay, and there are slots which are cut. This is a little exaggerated, but just okay to understand. Now from here to here, in between, the robot is actually blind, right, in terms of the encoder. Why? Because here it is 1 maybe, in between it is 0, then it is 1 here. Now in between here and here, the robot actually cannot see anything because this whole region is 0 now. So if it is somewhere in between here or somewhere in between here, it cannot differentiate between these positions. Now, so the control resolution depends on, number 1, the encoder resolution, number 2, on the memory size. Now, depending on the memory size, it can store that many bits only. For example, let's take the example of a linear actuator. Okay, so this is easier to understand. We have a linear actuator which is moving, which can translate. Okay, so this fellow can translate, and the end effector can move from here. Let me say the total range of the end effector is from here to here, just for example. Okay, and this is 1 meter. It can go maximum 1 meter. Now, uh, every point in that 1 meter, how many points would there be? There will be infinite points. Now, those infinite points cannot be stored in the memory. Okay, so if it is having a 4-bit memory, then at most it can store only that many bits, 2 raised to 4 bits. Okay, so it will have to divide this 1 meter by 2 raised to 4 and then store it in that, store those locations only. So it basically means that it will not be able to store infinite points. It will store finite points, maybe this point, this point, this point, this point, this point, this point, and this point. This, for example. Again, somewhere in between these 2 points, it is blind because it cannot store those locations in its memory. So if the memory is of larger size, say 18-bit, 32-bit, 64-bit, then obviously it can store more numbers. But if the memory size is low, then it can store a finite number of points. Now, even for a large memory size 64-bit system, even then it's not infinite points, it's a finite point. And between those points which it can store, it is blind. Okay. So these are 2 things we see that causes the control resolution. One is the encoder problem. Number 2 is the memory size. Apart from these 2, which are very much inbuilt in the control system, there is nothing you can do about it. Okay. So the other is sensor noise. Now sensors tend to pick up noise. This encoders or other kind of sensors which are working in the robotic system will tend to pick up noise from other sources, and that will tend to cause errors in measurement or in control. Mechanical errors. Now there are errors due to manufacture of parts. For example, when we are saying this robotic link is 1 meter, I just said that this is 1 meter in length. Okay, it can traverse 1 meter rather. Okay, but exactly this link may not be 1 meter. What I mean is that when the link is being manufactured, there is going to be some fits and tolerances. Now, because these tolerances are there, there will be some plus minus 0.01, for example. This is very small, but it is still there. Okay, that means there are going to be mechanical errors because of manufacture itself. In terms of, in case of assembly, there is limits and fits. In case of tolerances, a part can be a little bigger or can be a little smaller. Okay, so mechanical errors are there inbuilt in the system, and you cannot do anything about it. They are going to be there. Then gear backlash. When we talked about our control system and we derived our transfer functions, we saw that a motor has a encoder at the back for position sensing, and it has a gearbox in front for decreasing the speed and increasing the torque. Now this gearbox will have gear backlash. Now what is gear backlash? Gear backlash is something like this. We have a gear tooth. Okay, so this is a gear tooth, and there is a corresponding gear tooth on the other side, on the other gear. Okay, so this is the other gear, and there is a gear tooth there. Now, and there is one more tooth here, let's say. Okay, this is one gear, this is another gear. So this is one gear, that's the other gear. Now, you can see very clearly from here that there is no tight fit between the 2 gears, between the 2 teeth of the 2 gears. So what we can see here is that there is some gap here. So when it is rotating on this side, the moment it tries to rotate, there is some free motion here, and that is your gear backlash, and it is directional. Okay, so for example, if this is rotating this side because there is contact there, there is no backlash. But the moment it reverses and goes that side, immediately there is backlash. And you cannot do anything about backlash. It has to be there because gears cannot mate completely. Okay, it will jam otherwise. Stiffness. Stiffness of the links. For example, in this figure I drew here, suppose there is a mass mg here. Okay, because there is an overhang of 1 meter, what will happen is this will tend to bend a little bit. So it can deflect in this direction. Because this is not ideal rigid body, it will have some stiffness irrespective of how strong it is. It is going to have some amount of flexibility, and because of which it will have a little bit of deflection. That is the effect of stiffness. What about wear and tear? Now a robot is going to work for very long. Okay, normally it works for almost 5 years or 10 years. So for 5 years, if it is operating in 3 shifts in an industry, picking up heavy weight, all kinds of temperature, wear and tear conditions, the joints are going to undergo wear and tear. Now, if the joints are going to undergo wear and tear, what will happen? Things like backlash will increase, stiffness, there can be wear and tear on the bearings. Okay, so some shafts will become a little bit loose. Okay, then there are changes of temperature. There is a daily temperature change. Now, most of the robots are made of steel, right? Mild steel or metallic components, and because they are susceptible to changes in length with temperature change, some of the changes are going to be there in various joints. So if you say the link length of this robot is exactly from here to here is 1 meter, okay, there's going to be some change because of change in temperatures. Now, direction of motion. Again, this is very important and very interesting in order to understand the direction of motion. So, for example, if the manipulator is going with gravity or against gravity, suppose it is going that side or it is going this side. Depending on that, it will bend this side or it will bend that side. So, direction of motion is to do with dynamics of the system. So, dynamic forces are going to determine which side the deflection will come. Okay. Speed of operation. This is again dynamics. So, if you are operating very fast, the dynamic forces are going to be very high, and because of which there is going to be more deflection on the links and more stresses will come on the joints. So, all these parameters we see are not in our control. So, we have done a theoretical analysis of control systems. We have done theoretical analysis of forward kinematics, inverse kinematics, assuming that everything is ideal. If you want the robot to go to one point, we can do inverse kinematics, controller can take it to that point. But then we'll see that because of these errors which are there, and we cannot do anything about these errors, it will not be possible for the controller to take it exactly there. So let's see how we specify robotic system. So the first term is the control resolution. The smallest incremental change that the control system can distinguish is called the control resolution. So as I explained, there is one point here, another point here, another point here, another point here. These are points where the robot can go. Okay, it cannot go anywhere in between. Now this may be because of the encoder problem we saw, the blind region in the encoder, or because of the memory resolution, or because of the memory limitation. Okay, so it can go here and it can go here, and this much distance is called the control resolution. Okay. Now, on top of this control resolution, it also has mechanical inaccuracies, okay, and sensor noise. So when it's worst case distance between two adjacent points. So if you want to go to this point, although the control resolution can take it there, okay, because of this mechanical inaccuracies which are building on that, which is sitting on top of that, okay, what will happen is it will not go to this point, but it will go somewhere near this point. Okay, so this is my spatial resolution now. Okay, so what will happen is it will not go exactly to this point. It may go somewhere here, it may go here, it may go here, but it's a region around that point. So resolution is control resolution and spatial resolution. So the manufacturer has to actually specify the control resolution and the spatial resolution of the system. Now, accuracy is a measure to approach an arbitrary point in space previously never approached. Okay. Now we have seen that our control resolution is here, 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 and here. That's the control resolution where the system, again, theoretically the robot can go. But when you want the robot to go to a point, maybe I want it to go to this point 1, what will happen is when it is trying to go there, there are mechanical errors which are sitting on top of the control resolution. All kinds of errors like backlash, stiffness errors, okay, wear and tear. So what will happen is, now let's say it is going somewhere here. I want it to go here. So we have seen that it will not go there, but it will go somewhere near there, either this side or this side, depending on from which side it is coming. If it's coming from this side, it will go there. If it's coming from this side, it will go here. So what it did is, you are supposed to go to this point, but it went somewhere on the right or it went somewhere on the left now. Okay, and this is because of all the errors that we talked about, and plus the control resolution which is there in the system. Okay, now this is my control resolution. Okay, and the accuracy would mean that, so if it is coming from the left hand side, it will go somewhere here, or it will on the right hand side, it will go somewhere here, and this is half the control resolution. Okay, so it is half control resolution. So what we say is this distance is half the control resolution. So this is half control resolution. Okay, so accuracy is a measure to approach an arbitrary point in space previously never approached, and when it is trying to go to this point, point 1 here, it will either go to the right or to the left because of all the mechanical errors and control resolution. So accuracy is equal to half the control resolution. Why half? Because it can either come from the left side or the right side. So whichever side it is nearer, it will go on that side. Okay, so if it is not nearer to this point, then it is nearer to that point. Okay, so it is essentially half distance between the control resolution. So we have seen these two terms. One is the control resolution, the second is the accuracy, and accuracy is defined as equal to half the control resolution. Now we are done with control resolution, which is inherent because of the encoder and the memory size, accuracy because of all the other errors that are there, mechanical error, temperature, this, that. Okay. Now, apart from this, a robot is going to move in three-dimensional space. Here I have drawn only 1D. Okay, so I've just drawn one line and I've put some points. Okay. In reality, this is actually the work volume of the robot. So it can be like this. Okay, so it can be the work volume of the robot. So in 3D, it can be anywhere. Okay, so basically what it means is that this directionality of the errors also depend now. Okay, so there is another term which is used, is called repeatability. Now, ability of a manipulator to position itself at a position previously taught. And this is because of wear and tear, temperature, stiffness, direction of motion, speed of motion. The previous errors were essentially mechanical errors. Okay, gear backlash and things like that. Okay, but here we are saying that it is because of wear and tear with time, temperature, stiffness, direction of motion, speed of motion will cause more errors. So now suppose we have a work volume. Okay, this is my work volume and there is a robot there. And this robot is moving, it's at this point. Now, I have been able to teach it to come to this point. Let me explain it like this. Okay, so this is my robot manipulator and this is my control resolution. Okay, these points are control resolutions theoretically. Okay, and accuracy is halfway between any point. Now, suppose I am using a program or a joystick and I program the robot to go to this point, but it is not going to that point, but it's coming here. Okay, so first attempt, it has come to that point. Okay, and this is my control resolution. Now, so that's my first attempt. Then the robot goes off somewhere else and does something else. Okay, now I want it to come back to this point again. Okay, now what we'll find is it will not come. It had come back there once, it had gone there once, but when I want it to go back the second time, it will not go there, but it will go somewhere near there. It'll go, if it's coming from that side, it may go here, it may go here, it may go here. It's in 3D. Okay, so repeatability means the ability of a manipulator to position itself at a position previously taught. That means it did go there in the first shot, but in the second time, third time, fourth time, it will not go exactly there, but it will go somewhere near there. And why is that? Because of parameters like wear and tear, direction of motion. If it's coming from this side, or it's coming from this side, or it's coming from this side, depending, these errors will keep changing. Okay, depending on the side also now. So what we see is that if we have gone to this point once, this is my first attempt. Okay, the second, third, fourth, when I go, I'll go somewhere near there. This is in 3D. So at the end of the day, what will happen is, if this is my desired position, I'm getting a region in space in which at every attempt the robot is going and positioning itself. Okay, and then what do? We take the deviation and we take 3 sigma of the errors, and then say that this is I'm able to teach it here, but it is not going back there, it is going somewhere near there. And what is the range inside which it is going to go? It is going to go within 3 sigma, and this is basically called my repeatability. Okay, so there are 3 kinds of errors that we have seen. The first kind of error is because of control resolution and memory size. Okay, the encoder and the memory size. Then things like mechanical errors due to manufacture of parts, limits, fits, tolerances, backlash, things like that. So this is the one that causes, so this is the fellow that causes control resolution. This is the fellow that causes accuracy. Okay, and then we have the other kind of error which causes repeatability: stiffness, wear and tear, temperature change, direction of motion, speed, etc. So all these errors together make the robotic system not very ideal. Okay, so if you want the manipulator to go to some point in space, it will probably go somewhere near there, and that will be defined by this repeatability of 3 sigma. Now the manufacturer has to actually find this out. Okay, manufacturer has to, so manufacturer has to state these errors in the manual. So if you buy a robot, you'll find that these are stated. So for example, control resolution will be 0.01. So this is the smallest you can go. You can't go below that. Okay, so when you buy a robot, you should be very, very careful as to what these numbers are. So with a robot which can go at most 0.01, if you're trying to position at 0001, then this will not be possible. Okay, So this is what is the importance of control resolution, accuracy, and repeatability. Now, the manufacturer has to actually find this out. So how do you find this out? We have seen repeatability has to be experimentally observed. So what they do is, and the other parameter which I forgot to mention is that it depends on where you are in space. Okay, so in this particular case, I gave the example here. So if you're here, your repeatability will be different. If you're here, it will be different. If you're here, it will be different. Why? Because the errors behave differently in space. So the manufacturer has to actually do the experiment. So at this point, for example, they will come in multiple directions, and in each time he'll measure the errors. Okay, and for a very large number of times, and they have to do it everywhere in the workspace. Okay, so everywhere in the workspace, the manufacturer will do this experiment, and something to note is that it is time dependent. Okay, and because it is time dependent, it has to be done for a very, very long time, sometimes months. Okay, so the robot will be operating for months continuously, and at every point it will be going, and the errors will be measured, and then the manufacturer will give you the 3 sigma of those errors. So this is something that takes a lot of time, and this is something that adds to the cost of the robot. That's why robots are very, very expensive. It is not that the mechanical system is very expensive or the controller. It's only about 20% cost of hardware. Okay, the rest of the cost is all this repeatability, the software cost, the maintenance, then the performance guarantee. Okay, then upgradation, all that. So the hardware cost is only about 20%. 80% is all the other costs. Now we have seen these 3 terms that the manufacturer has to declare and give on the manual. Now let's look at a little bit of programming. Now let's look at this very simple example of a robot which is picking up a part from a conveyor and then placing it on this carousel in an indexing way. So the first thing is that when a part comes on the conveyor should be able to figure out that a part has come. So there has to be some sensor there, right? So there would be a sensor here which is going to figure out that a part has come. Okay, now after the conveyor figures out using the sensor that a part has come, it has to communicate with the robot. It has to tell the robot that a part has come. Now you go and pick it up. Now normally when the part comes, the conveyor will stop. It will inform the robot that a part has come, and the robot will go and catch the part, pick it up, and then maybe put it here. Okay, then after putting it here or after picking it up, the robot has to tell the conveyor that I have picked it up. Okay, now you please start again. So there has to be communication between the robot and the conveyor, and this communication is based on dependent on sensors. Okay, so we talked about sensors and actuators. So you need sensors which are in the robot, and you need external sensors also for a robot to work. And so this is a requirement that a robot has to interact with some other pieces of equipment. So there has to be some kind of communication. This is another example of a flexible manufacturing cell in which the robot is picking up an object from the parts carousel. Okay, then maybe putting it on work table 1. Then after machining is done, it is taking it and putting it in machine 2. Then it is taking from here and putting it here. Okay, so that's 1, that's 2, that's 3, and that's 4. Okay, sorry, 1, 2, 3, this is 3. Okay, now if you see this, there is a sequence. Now suppose the robot picks up a part from here, puts it here, and then one more part has come, the robot picks up that part, okay, and puts it here. Then one more part has come, the robot picks up that part also. Now you see there is a part here and there is a part here, and the robot is also holding a part. So now the robot has no place to keep the part, and there is no way it can pick up the part and put it in this drop point also. So what has happened is the logic, there was something wrong in there, and this is what is called a deadlock. Okay, so a deadlock condition is one in which the robot cannot do anything more. It is just locked in there. And if a deadlock happens, then what will happen? The full assembly line or the robot servicing equipment, whichever machines the robot is servicing, everything will go down. So robot programming is not only a question of writing a program, okay, that is going to pick up from somewhere and put it some other place, but it has to be efficient. It must be the fastest way of writing it. It must avoid any kind of logical deadlocks with other machines. Okay, So this is two things that we need to keep in mind when we are writing a robotics program. The first is communication. A robot has to communicate with other machines. Number two is it must be efficient, and there must be no deadlocks. Now, the general hardware of a robot consists of the mechanical hardware, which is the arms, motion transmission gripper, then the robot control unit, which is the robot controller, motors, power amplifiers, ADCs. Okay, this is the robot control unit. ADCs are analog to digital converters and digital to analog converters. Now, some of the software, some of the sensors could be analog, they could be digital. A lot of the sensors like ultrasonic sensors, these are analog sensors. So the output would be a voltage. Now it has to be converted to digital for the robot to understand. So in that case, it must have an ADC on board. The other that is the converse is the robot is giving information to something which is digital. It must be able to convert from analog to digital and then give a signal. Okay. Digital to analog conversion should be there. For example, if the robot is communicating with another machine using an analog channel, then it must convert digital to analog and then give it there. And then, so we have number one, mechanical hardware. Number two, robot control units. Number three is central controller for interfacing robot with other machines. So there has to be some controller for interfacing the robot with other machines. So a robot does not work by itself. Okay, a robot doesn't work alone by itself. It normally works in association with other machinery also. So it's very important to interface and for the communication to be there. Now, we can program a robot by using these two methods. One is a teach pendant. The teach pendant is used to manually teach the robot. And what are we teaching the robot? Basically, a robot moves in points, moves 2 points from point to point. So we are basically teaching different points to the robot. Okay. So for example, a teach pendant looks something like a remote control on a TV. Okay, TV remote you must have seen. So there is a display there, and there are joints, say 1, 2, 3, 4, like that. And there is a plus minus buttons are there, or a joystick is there small, sometimes buttons. So we can take the teach pendant in the hand, which is connected to the robot, and by pressing the joint number and plus minus, we can move corresponding joints and take the robot wherever we want. For example, if we have a robot here, the robot has to pick up something from here and keep it here. So at this point, we can use the teach pendant, take the robot till here, make it catch this, then take it here by just by pressing different buttons in the teach pendant. Okay. Now, wherever the robot is going to a point in space, it gets recorded in the memory. Okay. So basically, suppose the robot is here, it displays what is the position orientation of the end effector. So you can store it in the memory. So you can manually take the robot here, then pick up something, put it there, store these things in the memory, and then you can play back. Now, of course, this is not very efficient, and it can be done for very simple programs only. The other is program-based control. So the desired task is written as a sequence of motions in a language such as VAL. Okay, so this is like a computer program, C language or Fortran language, you're familiar with that. So this is a computer program in which the desired task is written as a sequence of motions. Okay, and these motions can then be played back like a normal program. So in industrial applications, normally it will be program controlled because it is interfacing with so many machines, other machines, and it is doing complicated tasks. Now, in terms of languages, there are 3 generations of programming languages. We saw that robots were essentially invented somewhere around 1960s. Okay, with the invention of the microprocessor came robotics and NC machines. Okay, so with the first robot that was made around 1960s, these robots were very simple robots. Okay, so they were very simple in the sense that they were only for pick and place operations and very limited interaction with the environment. So they did not have complicated sensors to interact with the environment like computer vision, then ADCs, touch sensors, force sensors. They were simply made to pick and place applications. And this is the first generation of robots. The second generation is essentially interaction with the environment. And we saw in the early classes that this is essentially because the computer became more and more powerful. So for second generation robots, we had more powerful computers. Okay, so as the computers became more and more powerful, it could control and interact with more number of sensors, and that is our second generation. Interaction with the environment, force, touch, ADC, DSC, etc. Computer vision, all these are second generation. Third generation is where we are today. Okay, so second generation is about 1970s. This is about 2000. Okay, so third generation is basically intelligence capability to understand general commands. For example, robot programming is very expensive, and there are specialized people who do that. So suppose the robot can understand general commands. General commands means the way we speak. For example, if the worker could tell the robot that pick up this nut and put it there and tighten the nut, so it should be able to understand what is tighten a nut. Okay, but the problem with English language is that it can have different meanings in different contexts. It is very context sensitive, because of which till now we have not been able to have machine language understand human commands, human general commands, especially in manufacturing. Okay, for example, if it has to do a particular task like spot welding, spray painting, then tighten this, pick this up, assemble something. If you simply say assemble part A and part B, it should be able to understand, but then it won't. Okay, because it is very context sensitive. So this is where we are today, and most of the research is focused on intelligent programs or learning to understand general human commands. Now, examples of few programming languages. The earliest programming language was VAL. So this is called Victor's Assembly Language. It was developed in 1960s, and it was developed by the Unimation Corporation for the Puma robot. Puma is primary universal machine for assembly. So when we looked at the inverse kinematics, we studied the inverse kinematics of the Puma robot. Now, so the company Unimation made the robot Puma, and they also invented the language which they call Victor's Assembly Language. Probably Victor is the person who developed that language. Now this language is based on the basic language. Okay, in those days simple computer programs were there, and the simplest is basic. Now basic language, as you must have studied in school, is it has a line number, then it has a statement, then it has a line number again, statement, like that. Okay, so the structure of VAL language is also like this. Now with time we have had VAL 1, VAL 2, and most of the industrial robots today, 95%, use some derivative of VAL. So the commands are more or less similar. So this is one which is still there, and as it is used 95% of the case, we'll be studying VAL only, VAL 2. The second language which was developed around 1960s was AML. It was developed by IBM for manufacturing automation system. Okay, but IBM since then has closed their robotics division, and they don't manufacture robots anymore. So this language is not used anymore. Okay, but this is basically for assembly automation or automation systems. Now the third language that was there was RPL, and RPL is based on the Fortran language. This is also 1960s. So most of the companies which are using RPL have since closed down. Okay, so AML, RPL, these languages are no more there. In fact, the company Unimation has also closed down, and it has been bought over by Kawasaki. So Kawasaki is the one that makes the Puma robot now, although it is not in production anymore. So the only surviving language is VAL, and we will look at VAL 2. Now the basic commands in VAL 2 language consists of these four parts, or the basic program rather in VAL 2 is made up of these four subsections. So the program starts by definition of constants, variables, and data objects. Constants, you understand what are constants. Okay, for example, pi is 22 by 7. This is a constant, or 3.1415. Okay, so this is a constant. Okay, so constants have to be defined first, then variables. Suppose there are different variables which are used. For example, names of points. Say P1 is point. Okay, so variables you have to define. Then data objects, if you're using data objects like in C language, then you have to define them. So the first thing in the line, what are the constants, variables, and data objects we can define. Now variables can be names, variable names which are assigned different values. That also is a variable. The second part of the program is the motion control commands. Now a robot moves around in space from one point to another point, okay, when it does the task. So the second part is the motion control commands, which are going to move the hand or the end effector from one position to another position. The third set is robot hand control. Now robot hand control, unlike a NC machine or other machine, a robot has a gripper. So it has to use its hand, for example, open the hand, catch something, close the hand. So there is robot hand control. And the third is the program control and input output control. So program control and input output control is essentially for logical statements, because you need to go to a subprogram, for example, or you need from one line we can jump to another line depending on some condition. So if this condition is true, then it goes back, or if condition is false, it goes forward. So we need some program control, which is basically logical statements. Then input output control. So a robot has to communicate with other machines. So there has to be some input and there has to be some output. Okay. Input to the robot and output from the robot to other machines. So these are the four parts of the program: constants, variables, data objects, motion control commands, robot head control, program control, and input output control. So the first thing we are seeing is variables and motion control. So the first variable is a point. Okay, point is P1. This is the variable name. So this is the variable name. Okay, variable names can be letters. Okay, they can be numbers, a combination of letters and numbers. So it depends, 8 characters or 10 characters depending on the version of the robot. So point P1. So this is a point P1. The variable name is P1, and this points to the end effector location. The X, Y, Z is given here, and theta, alpha, and gamma are the orientation. So this is position of end effector. This is orientation of end effector. Okay. So point P1 indicates a point of the end effector where the position of the end effector is 3, 4, 5 X, Y, Z coordinates, and the angle, orientation angle, is theta, alpha, gamma. Okay. Now, so a robot essentially moves from point to point to do a task. So I have a robot here. Okay. It has to go to this point, then it has to go to this point. Okay. So we have to define this as P1, then we can define this as P2, and like that. So at these points, we have to define the position and the orientation. If you don't write the orientation, then there is a default. Okay, so whatever was the orientation, it will probably keep it there. Okay, so either we give all 6 or we give only 3. Now, after defining points in space, we have to move to those points in space. So the first command is move P1. Now, just like in English language, it has been made so simply that anybody can understand a robot program very easily. So move P1 means move to the point P1, and we have already defined P1 here. Okay, so it simply moves to the point P1. Now we have an interesting question here. Now the interesting question is, suppose I'm here and I want to go here. This is my point P1, and I say move P1. Okay, so I say move P1. Okay, so how it is going to go from there to there? There are 3 degrees of freedom here, so there is 3 DOF arm. Okay, is it going to go in a straight line? Is it going to take a curve? What is it going to do? Okay, so for example, if you just think about, if you don't think and simply answer, you're likely to say that it will follow a straight line. Okay, well, that's the wrong answer. Okay, so what it will do is it will find a path which minimizes the energy requirement. Okay, so what it will do is it will find a path. It is going to find a path, okay, which is going to minimize energy. So this path will basically be at the joint level. Okay, we saw in our trajectory planning that the trajectory is fitted on the joint, not at the end effector. Okay, so what it will do is energy requirement is proportional to the number of joints that move to take the end effector from one point to another. So it basically means that it will move the smallest number of joints so that it will take the end effector from this point to that point. So if only one joint is enough, it will move only one joint. Okay, so this is also called least motion norm. And if you observe human motion, we also follow this. Please observe very carefully the next time you pick up an object from a table or from anywhere, or when anybody is picking up, you notice the motion of the joints in the arm. Our arms have 7 degrees of freedom. 3 at the shoulder, 2 at the elbow, and 2 at the wrist. But when we are picking up an object, you find that it is normally the shoulder which is moving and the elbow, but no other joint is moving. Okay, so that means that even we minimize our energy by moving such that the minimum angles are moved at the joint level. So it is not a straight line. Now, why is it not a straight line? It's also easy to understand. What is a straight line? A straight line will be made up of infinite points, a very large number of points. So if the robot has to follow this straight line, it has to do inverse kinematics at all those points. Only then it can go there. So to do inverse kinematics at a lot of points, it will take a lot of time and it will take a lot of energy. Okay, so robots normally don't move in straight lines. Okay, from this very simple reason. Now, but there are applications where you need to move in a straight line. For example, if you're catching this object, this robot has to catch this object, then you should come down straight and catch it, and not try to go from the side. Okay, this is not done. The other application is, suppose we're talking about assembly. So I'm going to assemble this part inside this part. Okay, so I'm assembling this part inside this part. So it basically means that I need to move in a straight line. Okay, and especially in electronic assembly, in electronic assembly, you notice that on the motherboard the chips are fitted, and the chips, computer chips, have very thin legs. They have a lot of legs, and they have very thin legs like that. So when these chips are inserted, the motion has to be exactly straight. Otherwise, what will happen? The legs will break. If it goes in an angle, the leg will break. So this straight line motion is required for assembly and for many applications, pick and place, etc. So in order to have a straight line motion, there is another command which is moves. So this S, MOVES. So this S basically means that move in a straight line. So this has two commands, move and moves. Move is only to give you the least energy node, and moves will take you in a straight line. So again, going back here, if we just say move P1, what trajectory will it take? It will probably take trajectory like this. Okay, so it will simply take a trajectory like this, okay, curved trajectory normally. Okay, if we say move, if we say moves, then it will go in a straight line. Okay, that is why we need two commands depending on what the robot is doing and how much energy consumption is there. Say, for example, if the robot is somewhere else in space, it is here or doing something else, then it has to come here, then it has to come here. So you can combine your move and move statements such that you use moves only when required, not otherwise. Now the other command is draw. This is an incremental command. Suppose we have come to the point P1, which is given by 3, 4, 5, and it has come to this location. Okay, and suppose this location is not correct, that we have said 3, 4, 5, it has come there, but because of error or whatever, it came somewhere near here. Okay, so the end effector has come here. Now I want to make a small correction. So this correction is this small draw which says move this in the X direction, Y direction, Z direction. So now it will make a correction and it will go there. Okay, now so we have seen move, moves, draw, approach, and depart. Now approach basically means you are approaching a point P1 and keeping a distance of 50 along the Z axis. So when a robot picks up something, okay, this is my, let's call this P1 now. So this is my point P1. Okay, so basically it will approach this point P1 and keep a distance of 50. Okay, from this point P1 in the Z direction. This is my Z. Okay, that's my Z direction. So approach means approach the point P1, keep a distance of 50 along Z axis. So when you are catching an object, normally the robot will be using the approach command to bring the end effector near the object before we catch it. After catching, the same thing, it goes up straight. Okay, and that is command depart. So depart P1 50. So it basically means after catching the object at P1, go backwards along Z by 50. Okay, so this is for catching, this is for departing. Now let's come to open and close. So we have covered. So as you can see, robot programming is very, very easy, and it has been made like this such that users can use the robot easily. Otherwise you'll need to take a course in robotics and nobody is going to buy a robot. So we have looked at constants, variables, we have looked at motion control commands, okay, and then we will look at robot hand control commands. Now in terms of hand control, okay, There is the open and close. Now let's write a very simple program here. So this is part which is kept here, and this is my point P1. Okay, P1 is already taught. Now the robot manipulator is somewhere here. It is doing something. Okay. Okay, it was here doing something. Now I bring the robot manipulator till here and position it there like this. Okay, then I bring it down, catch this object, close the gripper, and then go up again there. So I'm writing a program. Let's call this point P2. Okay, so I say move P2, so it goes there. Okay, then I say open. Okay, then I say open. Then what I say is moves P1. Then I say close the gripper. Then I say moves P2 again. Okay, line numbers 10, 20, 30, 40, 50. This is a simple program I've written. So move to the point P2. I could have also approached P2. I could have written approach P1, keep a distance of 50. The same equivalent command. Now after moving to P2, I say open. Then I say moves P1, so it comes down to P1. Then I say close, it closes the gripper. Then I say moves P2, it goes back. Okay, so this again can be depart. Okay, depart P150. Now, do you think that this program is going to work, or there is a chance of an accident here? There's a potential for an accident. Now, if you just look at this program, it seems like everything is fine. Okay, but there is a chance of an accident. Now, what is the accident that can happen? Now, if you look very closely and think how a program actually works, then the compiler will come to this line. Okay, it will execute the line, then it will go to the next line. That's how it works sequentially. So in this line, it says open. So the gripper is going to open, and the moment this line is executed, it will come to the next line and it will say moves P1. So in line number 20, the compiler will basically tell the gripper controller to open. Okay, and the gripper controller will take some time to open because it's going to physically open the gripper. Okay, but as far as the compiler is considered, this line has already been executed. Okay, so it will immediately go to the next line, and next line says moves P1. So when the gripper is opening, the robot is already moving, because as far as the compiler is considered, this line is already executed. Okay, similarly, after it has gone to P1, we say close, it closes the gripper. So the compiler will execute this line and say close, which means it will give a signal to the gripper controller to close. But that closing will take some time. If it's a pneumatic gripper, it is going to get the pneumatic pressure, then the gripper is going to close slowly. Okay, but the compiler, after executing this, will immediately move here, and it has also started moves P2 now. So as the gripper is closing, if you can imagine, the gripper had come here. As the gripper is closing, this is also moving. Okay, and so in the first case, there is a chance it will hit the object. The second case is it will not catch the object at all. Okay, why? Because opening, closing of gripper, so open, close takes time. Okay, so this is something that we need to keep in mind. Now to avoid this situation, this command open I is there and close I. Open I means I means immediate. Okay, so it means or this is also a closed loop command. Okay, which it means that only the compiler will first execute this, and it is in closed loop. So only after it has opened, then it will go to the next line. In terms of closed, it is first going to close the gripper, and after it is completed, then only it will go to the next line. Otherwise, it won't go. Okay, so open I and close I are closed loop commands, and they are used for catching objects when you are catching an object and when you are departing from it. Now, in some cases, So you might be wondering that then why not always have open eye and always have close eye? Okay, why have open and open eye, close and close eye? So if the robot is just moving in space, okay, going from one point to another point and not doing specific pickup applications, then we can simply use open. Okay, so when the robot is moving, it's also opening. It's okay, there's no problem. Now why that is important is because opening and closing takes time. It's a pneumatic controller, so it is going to take some time. And in a robot, even a fraction of a second is a lot of time. Why? Because if the opening is say 0.5 seconds and the robot is going to do 10 to the power 100 operations, then you know what will be the error time, what will be the time saving now. So if you can save in a small amount of time, because a robot does millions of cycles, you can save a lot of time. So when the robot is not catching something, moving in free space, we can simply use open or close. And when it is going and catching something, then we can use open and close, open eye, close eye. Now the other command is close eye 75. That means if you can control the amount of which the gripper can open. So this is my 75 now. So it will close till 75. But most grippers are just open close. You can't control the. Now, so I just explained why two commands are there, open and open eye. That is essentially for safety purpose when a robot is moving, or in terms of open loop, a closed loop command or an open loop command. The other commands that are there are speed IPS. IPS means inches per second. This is the end effector speed. It can also have meters per second. Okay, so meters per second. Okay, so MPS is meters per second. Yeah, this is also available. Define a path. For example, we want the robot to follow trajectory like this. So I give it a point A1, I give it a point A2, and I give it a point A3. And the robot will follow this trajectory. Okay. Pause and delay. For example, the robot can go and pause for a few milliseconds. This is something like a delay in a computer program. Okay, in a microcontroller program, you have delay by delay 1000 milliseconds. Okay, so this unit is milliseconds. So if I say pause, pause thousands, pause 1000, then it will pause by 1000 milliseconds. Okay. Now, a robot has to interact with other machines, so there has to be communication. And a robot can communicate, should be able to communicate with other machines in such that it can work synchronously with other machines, okay, to pick up, to place. And that is where the question of communication comes in. Now, communication is basically by means of channels. We can think about channels as wires. So there's a wire which is fitted from here to here, and there's another wire which is fitted from here to here. So let's call this channel 1, let's call this channel 2. Electrical wires. So how this communication can take place is essentially by passing voltage. Okay, so if I pass a high voltage, say 5 volts in channel number 1, the robot understands that the part has come. Okay, and after it has picked up the part, it will make this 5 volts on channel number 2. So now the conveyor understands that the robot has picked up, so I should start again. Okay, now another interesting feature here is, suppose in this problem the robot has to pick up from here and put it here, like that. Okay, so the robot has to put one part in each of these boxes. What will be the fastest way to do this? Should it go like this, then like this, then like this, then like this? Would that be fast? Or should it go like this, then like this, then like this, then like this? Or should it go any other way, like this? Okay, or like this? Which will be the fastest way? Okay, how do you answer this question? Or the more interesting question is that would there be any difference in time? Or irrespective of how it does it, the total time taken is going to be the same. Okay, so total time is equal to sigma of all the times, t1 plus t2 plus t3 plus t4. So would it make any difference in what is the sequence in which it does? Because it has to go to every point once. Okay, so the total time is likely to remain constant. So this is something interesting to note. So in the next class, what we'll need to look at is communication. How does a robot communicate with other machines? And the communication can be for other machine tools, this is a simple case of a robot. Okay, a robot just simply picking up a part and keeping it somewhere by means of a conveyor. But it could have communication and it could have logic with a lot of other machine tools which are there. Okay, so in the next class, we'll look at how communication takes place between a robot and other machines. And then what we'll do is we'll look at an actual robot program which is going to pick up a part and do indexing. So we'll stop today. Thank you.